Right ones. That one. I think it might be. Let's find out. Good. Sharing the right one, Thomas? Not sure we're sharing the right screen. We're good? Okay, great.
Is that working?
Right. Well, this next introduction gives me great pleasure. We were talking earlier about the importance of having early career people get involved early in mission studies. So Maria Goof, some years ago, was a postdoc here in this early studies of a thing called at the time AFTA, then W first, now Roman. My pleasure to welcome her back. Maria is now a technologist, a scientist at JPL, and will tell us about how Roman will be preparing us for Habitable Worlds.
Thank you very much, Marshall, and thank you for having me today. It's a pleasure to be here to talk about very high contrast imaging in space with the Nancy Grace Roman Space Telescope chronograph and how it may enable precursor science for the Habitable Worlds Observatory. Okay. So the Nancy Grace Roman Space Telescope will be launched in 2026 with an onboard technology demonstrator to demonstrate exoplanet imaging in space. The Roman chronograph will be capable of detecting and characterizing exoplanets and circumstellar disks in the visible at contrast down to 10 to the -9, which is several orders of magnitude better than the current state-of-the-art chronographs. And the Roman chronograph will be able to image radial velocity or RV planets and further enable their in-depth characterization. The plot that you're seeing here of the fluctuation star as a function of planet separation compares the predicted performance of the Roman chronograph to the performance of the current state-of-the-art chronographs. And so with that goal, the Roman chronograph will really be a stepping stone toward the future mission to image terrestrial planets in the habitable zone of their star, including the Habitable Worlds Observatory. And in addition, we'll be able to do some circumstellar environment as well in the visible and unprecedented contrasts. So achieving a contrast of 10 to the -9, it's all the more challenging that the telescope design has not been optimized at all with high contrast imaging in mind. And so for this, the Roman chronograph will rely on lessons learned from ground-based and space-based instruments. And on top of that, it will demonstrate some key technologies that will be used for the first time in space on a high contrast imaging instrument. So the Roman chronograph will be the first space-based high-contrast imaging instrument with active wavefront control, and its EMCCD detector will enable frame acquisition in photon counting mode to detect very faint signals. Okay, so the Roman chronograph includes several instrument modes. In the visible, spanning a range of wavelength from 545 nanometers to 870 nanometers, and it includes those, at least some of those modes, the narrow field of view imaging with in band 1 here with an hybrid Lyot chronograph. We also have slitless spectroscopy, low-resolution spectroscopy in band 2 and 3 with shaped pupil chronographs and a wide field imaging and polarimetry. mode with the band 4 with JWST chronograph. So it is important to note here that only one official mode will be fully tested prior to launch, which is band 1, this one with the Habitable chronograph, the imaging mode. And all the other modes are best effort, including 3 and 4 that are the priority mode after band 1. So, which is a good introduction to my next slide. Before diving into what will be the science capabilities of the Raman chronograph, I would like to draw your attention to the fact that the Raman chronograph is not a science instrument, but it's a technology demonstrator. So what does that mean in practice? In practice, is that it doesn't have any official science goals, but instead, the chronograph objectives and goals are driven by the requirement that Raman shall be able to measure the brightness of an astrophysical point source at contrast 10 to the minus 7, located between 6 and 9 on the OVD, and at a SNR synergy ratio higher than 5. So in practice, it doesn't mean that we're not going to do any science at all. I mean, any science-worthy observation, but what really drives the mission is that technology demonstration. So what does that mean in practice? So the Raman chronograph will be allocated 90 days during the first 18 months of this 5 years mission. It's a lot of numbers, so 90 days during the first 18 months to do its observing campaign. And the observing sequence looks like this. Here you have an initial setup, the acquisition of the star and the initial setup, followed by high order reference sensing and control. And we're going to have one or several cycles of observation of a reference plus target pair, and we can do as many as we want. And on top of that, we will have collection of calibration data, either before or after, those observation cycles. And what I would like you to look into is the actual time that a full observing sequence is going to take. A single cycle takes about 1 day, and we also, this is not including all the other calibration and setup and high contrast imaging, how the reference sensing and control. And where other high contrast imaging instruments spend several hours on a single target, the Raman chronograph will spend several days on a single target. And so it can be several days, and it can be up to maybe 1 week for spectroscopic targets. So it gives you an idea of how long this observation takes. And just to introduce the fact that here is the list of the potential target that can be observed with the Raman chronograph. And it's just to say that of all those very interested and science-worthy targets, we'll not be able to do everything during the tech demo phase. We'll have to be very careful about which target we choose because, yeah, we're pretty limited in time. So that means that if we want the Raman chronograph to be used as best as possible in preparation for the future imaging missions, we really need to think ahead about which targets we want to observe as part of the tech demo phase. So during the tech demo phase, what we're going to do is that we're going to observe a couple of known self-luminous young planets and observe them at new wavelengths. We're going to observe non-radial velocity planets and image them for the first time in reflected visible light. And we're also going to observe some non-debris disks. And opportunistically, it's hard to say, during the deep imaging of radial velocity system, maybe some exobodies and of course some calibrators, both for post-processing and photometry and astrometric calibration. And on top of that, we may, and it's not guaranteed at all for now, be able to have an extended mission if the technology phase is successful and we are pushing for it. We may be able to do some additional science on top of this, and I'm going to talk about this on the next slide. So I think I'm going a little bit fast. So plenty of time to talk about science. So yeah, here there are a couple of exoplanet science themes that we're going to look into, and that we may have the opportunity to look into if we have additional time. So first of all, as part of the technology demonstration, the Raman chronograph will take the first visible light imaging spectrum of a cool Jupiter-like exoplanet. And it's also, as I was saying, observe a couple of luminous young super Jupiter that we know and had on top of that additional wavelengths. And if the technology demonstration is successful and we have some additional time, we can envision doing some comparative studies of self-luminous young super Jupiter and observe and characterize their atmospheric properties, and also maybe doing some comparative studies of a couple of colder Jupiter, mature Jupiter, and measure their albedo. And one also other very important, interesting thing that can be done as precursor science for the future mission is observing in details some of the targets that we may want to observe with those future telescopes, and characterize them fully with their orbital solution and all their characteristics as preparation. Let's jump to the dig sign theme. So it's, Raman chronograph will not be exception. All the high contrast imaging instruments are capable to do a lot of great high contrast imaging science with disks, and Raman is going to be able to do the same. So we're going to definitely target a couple of disk targets, including debris disks, and maybe if we are lucky, we may be detecting some exo-D disk, and that component is a really important part of precursor science for the Habitable Worlds Observatory, because when we select our targets for the Habitable Worlds Observatory, we don't want to select a target with a very bright exo-D and it prevent the detection of an exoplanet, so that's very important. And there are also a stretch goal here. We were discussing about this earlier at lunch today, to detect and characterize a couple of protoplanetary and transition targets, transition disk targets. But that's a stretch goal because those targets are very faint and they are not in the range of magnitude where the chronograph is optimized at all. So that's why it's a stretch goal. All right, so this is a slide just to show you an example of targets that can be done using the Raman chronograph, and this is a slide that was prepared by JWST. So if you have any in-depth question about those targets, this target and including FOMO as well, I invite you to chat with John about those. But that's just to show you some example of all the known planets that we know already, and famous big bright stars are very good targets for this high contrast imager. All right, so just a couple of words to say that the CGI science capability will depend on, of course, the CGI performance. We don't know yet what the final performance is going to be, and also the time devoted to the chronograph observation. So as if we have additional time and we need to advocate for that, we will have more science return from that mission. And a community participation program will enable members of the community to engage in the technology demonstration phase. And actually, I have two more slides that I had to include this morning at the very last minute because, as you may know, we had a Rosie's call for a community participation program, including both instruments, the wide field instrument, but also the chronograph. And here I'm just going to talk about the part for the chronograph. And it's, as of today, it's now official. We can, the team has been selected, and we can officially talk about who has been selected and which program has been selected for the community participation program. And so, because it's this last-minute thing, I didn't prepare the envelope and all the thing for the announcement. But I'm happy to announce, if you haven't seen the results yet, who's going to be on the community participation program for this year. So these are all the programs that have been selected. And I just want to comment on this is that it's a proposed program, but these people are going to be included as part of the team and prepare and support the chronograph for the next couple of years in a collaboration with the project science team and also the international partners. All right. So one last slide to advertise the talk by Alex Grimbone on Friday, who's going to talk about what we can do, not only here, it was the really science part, what we can do in terms of science as precursor observation for HWO. But Alex is going to talk about what we can do in terms of preparing for HWO, in terms of technology demonstration and technology experiments. So I invite you to look at to attend that great talk on Friday. And finally, the summary is that the chronograph is really a stepping stone toward the future high contrast imaging missions and the Habitable Worlds Observatory. Only a subset of targets will be observed during the tech demo phase because we don't have the time to observe everything. So, and also, only one mode will be officially supported. And so if we want to use the other modes, it will be nice to have an extended mission. On top of that, extending the Roman chronograph above its tech demo phase is one of the best opportunities we have to prepare for the Habitable World Observatory science. And we should take advantage of this opportunity and start getting prepared for this. That's it for me. I'll leave you with the timeline and I'll take any questions.
Thank you so much, Marie. We will start with questions in the room, then we'll go online. Questions in the room. Also, while we're doing this, we're going to do poster pops next, so poster presentations, and the speakers sort of line up along this wall in order. But questions in the room for Marie? I see one here. And again, I'll ask folks to introduce themselves.
Jennifer Wiseman, NASA Goddard, and maybe you said this already, but can you do an observation with the chronograph at the same time that Roman is using its wide field camera to do other science? No, it has to be one or the other.
I haven't told that, but no, we cannot do that. One thing we can do is for example, a couple of calibration that we can take while the wide field instrument is dark, for example, or kind of thing. So we're going to gain some time with that, but we cannot do.
Understood. Thank you.
Other questions in the room? Are there questions online? I think we're all looking forward to seeing Roman on sky 3 years from now is not a long time. I look forward to the first Science with Roman conference that we'll be having in, 4 years from now? So it's very exciting times. Thank you again, Marie. All right, there's a list of the order for the poster pops.
We're just going to go according to the order that they're in the PDF here. So.
Great. We're going to go following this PDF here. I think it is the order that was done in the, if you look in the Slack, you can see that order has been posted there by Neil.
You want to have a 1 minute timer?
I guess I can have a 1 minute timer.
Hi, can you hear me?
Yes.
Okay, cool. So, hi everyone, I'm Oscar Carreon Gonzalez. I'm a postdoc at the Paris Observatory in France. And my poster deals with the Large Interferometer for Exoplanets, LIFE, which is a mission proposed to directly image low-mass temperate exoplanets in thermal emission, that is in the mid-infrared. So this is a topic, by the way, that was given high priority by the European Space Agency's YS 2050 report. And in the paper and the poster that summarizes it, we compute which of the currently known exoplanets are potential targets for life in the mid-infrared, but we also compute which of these exoplanets are potentially detectable with the Habitable Worlds Observatory in reflected starlight. So we discuss the potential signs that we could get if we get both multi-wavelength observations. And I'll be happy to discuss on Slack if you want to, or I think there are some co-authors of the paper in person over there as well.
All right, we're going to move on. Thank you.
Thank you. All right.
Next up is Miles Curry.
Yeah.
All right, so hello everybody. My name is Miles Curry. I am a grad student entering my final year at the University of Washington. And my poster this week is on exozodiacal dust and how it may impact our ability to detect Earth-like exoplanets in direct images. And specifically, we're looking at some of the worst-case scenario mean motion resonance structures that can form at the orbital radius of an Earth-like exoplanet. So one of our main conclusions in this poster is that we think we may be able to mitigate exozodi for systems with about 10 zodies or less and for about 60 degrees of inclination or less using a high-pass filter and PSF matching technique. And also for, based on recent observations, we think we may be able to mitigate exozodi for potentially most nearby systems, even if these systems exhibit some of the worst-case scenario disk structure. So I'll be around all week if you have any questions or if you just want to chat. Just come find me, and thank you, and I look forward to meeting with you.
Mike, to the next one.
Hi, I'm John Debus, and I'm the lead of the NASA ExoPag Study Analysis Group number 23. You heard Natalie talk about SAG 22. SAG 23 is looking to see what the open questions still remain about exozodies, so things like Miles's poster are very relevant to us. We are in the process of trying to write a final report on some key study areas, so if exozodies are of interest to you, come talk to me. If you want to join in, we still have things to do, so you can join us even though we're sort of halfway done. And I would like to advertise that we are going to have a workshop here at Space Telescope in September, right after the JWST conference. It's going to be one day. It's an excellent opportunity for you to influence the final report if that's of interest to you, or to present late-breaking results to us. Thank you.
Hello, everyone. So my name is Zoe DeBurs. I'm a second-year PhD student at MIT, and I'm working mainly on trying to improve our precision of radial velocity measurements using different kinds of methods like machine learning methods as well as simple linear regression methods. Generally, this work is relevant to the Habitable Worlds Observatory because we hope that by measuring these masses more accurately of these planets, we're able to identify more Earth twins or super Earths and able to greatly increase the efficiency of Habitable Worlds Observatory by identifying these targets prior to the mission. Generally, we've applied these methods to a set of different FGK stars, which you can see a couple plots of here. And generally, we find that we're able to increase the RV precision by about a factor of 1.7, sometimes a little bit less. But we're optimistic that as we expand to a larger target list, that we're hoping to see similar amounts of increase in precision. But if you have a star that you want me to look at, please let me know. Come find me. Come chat with me more. Happy to be here all week and chat with people.
Right.
Hi, I'm Emily Farr. I'm at the grad student at the University of Colorado, and my poster is over some of the very cool thin film optics that we're doing right now. So one of the big challenges that we see in UV is both obviously getting our light and suppressing, in this case, Lyman alpha. So one of the filters that I'm going over here we're looking at is F110. And as you can see on this, our wavelength throughput for this is roughly about 50%, and at Lyman alpha is incredibly low for initial things. The secondary thing that we're doing right now is environmental degradation testing. So basically, I'm murdering these entirely to death. For those of you who have worked with lithium fluoride, you all know that it's incredibly sensitive to humidity. And if you look at the charts on the bottom here, we look at the very first measurement of the F110, and then the red over there is how badly it's died after 3 weeks and humidity at 70%. If you all have any questions or want to talk to me about it further, please come find me.
So,
my name is Megan Jaluka. I'm a rising third-year student at the University of Washington. As David Singh and Emily Hinkle demonstrated really well this morning, to prepare for HWO, we will have to leverage tools and data available to us now in order to better refine our evolutionary models and apply those to HWO targets of interest. This will be particularly important for understanding key processes such as atmospheric escape, ocean loss, and changing stellar conditions. And so I demonstrate these ideas and how we may leverage data from JWST through a statistical study of the TRAPPIST-1 system, as TRAPPIST-1 represents an edge case of the most extreme thermal escape during the pre-main sequence phase of the host star. And finally, I apply this escape model to a K-dwarf analog host for a Venus analog planet and compare that to TRAPPIST-1 to show that oxygen production may be more prevalent with the K-dwarf host. Thank you.
that's not you?
I'm thinking the next one.
Missing someone?
I don't know who
Okay,
that
we
is.
have the speaker's online, I think. Do we have a speaker for this slide?
This one doesn't even have a name on it. We'll deal with this one later.
All right.
Let's go on to Gordon.
Very good.
That's me.
Yep.
Hi, everyone. My name is Kenneth Gordon. I am a graduate student at the University of Central Florida. And my project really focuses on highlighting the importance and the benefits of using polarization to characterize terrestrial habitable exoplanets. And so in particular, we modeled 7 different epochs of Earth throughout its evolution, both non-habitable and habitable periods. And we show that polarization does impact the resulting signals, and when it's combined with the flux, the reflected flux from the planets, we are able to actually distinguish between those different habitable and non-habitable periods of Earth, especially when we start to incorporate the effects from the clouds and the hazes in our models. We show that, similar to the talk that we just heard, that the polarized phase curves show very clear signs of the clouds and the hazes. And so we can use these to help differentiate the different planets and to provide constraints for observing habitable exoplanets with HabWorlds. So thank you.
Right.
Hi, everyone. I'm Alex Greenbaum. I'm part of the Roman Science Support Center supporting the coronagraph instrument at IPAC. And I'll keep it short. If you'd like to learn more about what Roman coronagraph operations will look like, what the data products will look like, come find me. We can talk about the poster. I can attempt to explain the very complicated diagram on the right, which shows the many possible configurations of the Roman coronagraph. And of course, you can also look for Marie, who gave a great talk about Roman, and I'm going to talk about this also on Friday at the Tech Day. Thank you.
Hello, I'm Alex Howe. I'm a postdoc at NASA Goddard, and I'm presenting a project in which we quantify the scientific return of using an energy resolving detector on HabWorlds over the current baseline of the LUVOIR and HabEx final reports. Short version, we modeled a population of exoplanets with the ExoVista code. Check out the how-to tomorrow. We simulated a survey on those planets to figure out how many spectra we get, and the advantage of an energy resolving detector is that it takes spectra all the time, so we get a lot more of them, and that's what we were computing here. So check out my poster to learn more, and I will also be giving a talk about it on the Tech Day on Friday.
All right. All right, this is our logistical attempt at the very limits of possibility. Sydney Jenkins, are you out there? This is one of the people on the train trying to get in. So if we didn't make it, then all right, well, they're in tunnel right now, so we're going to move on and try to catch them at the end of this.
Hello. So I'm Shingo Kamida, the professor in Rikyo University, Japan. And my poster is on the new mission, 60 centimeter UV space telescope, recently selected as the JAXA's M-class mission number 6. And so this part shows some our scientific goal and also the objectives. And this part for the so you can see the specification and also the schedule and technology development. And the last part is about observation of exoplanetary atmosphere. So in our model, so we can see please ask me a question, but so you can see the feasibility of the observation of exoplanetary atmosphere. So please talk to me. Thank you.
Thank you.
Hi all, I'm Brad Koplitz. I'm
Is this
from
another?
Arizona.
Hi, Brad. Okay, there you are. Go ahead.
Hi, I'm Brad Koplitz. I'm from Arizona State University. So I represent people talking about gas in between galaxies, known as the circumgalactic and intergalactic medium. Ultimately, we can talk science all week, but I just wanted to highlight that I'm here to advocate for an oxygen 6 absorber detector in UV spectrograph. Thank you.
Very good. Ravi, sir.
Okay, thank you. Hello, everyone. So David Singh pointed out in the morning that one of the science questions HabWorlds Observatory is going to answer, at least attempt to answer, is to see how common are Earth-like atmospheres in the local neighborhood. That includes us. We are in the Earth's atmosphere, right? So can we detect industrial civilization with HabWorlds Observatory? And so that field is called the technosignatures field, technologically active civilizations. Nitrogen dioxide is one of the industrial pollutant, and we did some work to see if the previous version of HabWorlds, 15-meter LUVAR, can actually detect NO2 or not. I'll leave you at that suspense. You'll have to come and talk to me about that. But there are just like, so we don't have to schedule separate observation time because we can do concurrent observation with biosignatures. We can use your telescope, your instruments, your methods, your resolution, and do our science also. So there are, just like biosignatures, there are false positives, and no single gas is a technosignature. So we are working on that. If you're interested in a technosignature seminar series that we are organizing in the last 3-4 years, let me know. There are super awesome talks. You will think they are science fiction, but that's actually science. So thank you.
Hi, you can imagine this was not my poster. I'm presenting, you can see Natasha's picture up on the left there. I'm presenting Natasha's grad student at George Mason University who's been working with our team for a while and is a big fan of the Barbie movie. She'd probably tell you all to go watch it. But she's done fantastic work with our group using Bayesian retrieval tool to look at the detectability of water vapor under different assumptions for SNR and the wavelength bandpass that you choose. So we've done a huge parameter sweep looking at how detectable water vapor might be across the visible wavelength bands. And we've found some really interesting results showing that you can actually detect water vapor at much shorter wavelengths with, of course, associated higher SNR than you might have expected otherwise. But the key is to figure out what our assumptions are about detecting water vapor and what our requirements are. So message Natasha on Slack to ask her more questions.
Thank you,
Great.
Ken.
Hello, I'm Mike McElwain, NASA's Goddard Space Flight Center, where I'm a civil servant scientist and lead of the ExoSpec technology effort. This poster that we're presenting this week is actually really just sort of a survey of what the spectrograph options are for the exo-Earth spectroscopy. So of course, that's the ultimate goal of the Habitable Worlds Observatory. We list some of the capabilities we think that are needed. Of course, this will be reviewed by the START and TAG teams once they're selected. And list here what the LUVOIR and HabEx studies implemented, and then compiled a table of the different options that we think are available. So I'd be happy to discuss with anyone, get feedback on this table, and hear your thoughts on how we should best do spectroscopy for habitable worlds.
Excellent.
Hi, my name is Isu. I work across the street at the Hopkins Rocket Group. I'm a grad student. So I am developing and testing a hydrogen absorption cell. So this will enable low Earth orbit UV observations in the far UV. So basically, it's very difficult to observe anything in the Lyman UV range because of how much the geocorona blows out the signal. And so the hydrogen absorption cell works such that you fill a chamber up with molecular hydrogen, you dissociate it into atomic hydrogen, and then it resonantly scatters the Lyman alpha from the geocorona. And so we're testing this. I want to try it in a rocket. Hopefully it'll work. Anyways, yeah, so if you have more questions, I can show it to you across the street if you want to see it. So, yep, next step, we're just going to do some spectrograph integration and try to take some spectra from it. But that's it.
All right.
Good afternoon, everyone. I'm not Ty Robinson. He's on his way here, but I'm Arno Salvador, a postdoc working at LPL, University of Arizona. So Ty is gonna, and I will also be happy to talk about it, a model that we developed that is aimed to do retrieval analysis on Habitable World Observatory framework. So basically with this model, it has been developed to run on a laptop very efficiently. And so you can switch many parameters such as instrument designs. So you can try several band passes, several signal to noise ratio. You can do 1D, 3D observations, transit spectroscopy, transmission, thermal emission spectroscopy, and reflected light. Yeah, I think he will show some validation and how we published a paper about using this model and the solar system observations to basically trying to see what we will be able to tell out of extrasolar systems. So one example of what we can do with this model, basically here, so we start with Earth spectrum. And what I've tried to do here is to assess the influence of prior observation. So basically running some retrieval analysis where you know different parameters. So one case where you don't know where you don't have any constraint on any other parameter. One case where you have constraint on the orbital parameters, and one case where you have constraint on orbital parameters and mass constraints as well. And so what we can, what I'll be happy to discuss with you is that when you have basically constraint on the orbital parameters, you get a pretty good constraint on the planetary radius. Yeah, I'll be happy to explain you more about the mass constraints. Thank you.
Hello, I'm Noah Tusho. I'm a postdoc at Goddard. And I'm currently working on a new input catalog, a preliminary input catalog for the Habitable Worlds Observatory, or at least trade studies for the Habitable Worlds Observatory. And my input catalog will contain contents from the test input catalog and Gaia DO3. And currently we have around 13,000 stars, and that contains all the stars from the curated XEP list. And we can see that our list does a good job of matching the stellar properties of the XEP list. And I should have said this earlier, but my list is primarily for yield calculations and trade studies for the HabWorlds Observatory. and there will be a different input catalog for the actual observatory once we finalize like the architecture. But this is a very early preliminary input catalog for the direct imaging for the Habitable Worlds Observatory. And come talk to me if you have any questions.
Hi everyone, my name is Maggie Beth Turcott-Stevie. I'm a senior undergrad at the University of Maine, and my research is on how we can better understand stellar variability and how to mitigate it for the purpose of HWO. The premise of my work was to conduct an extensive literature review of research that has been done pertaining to stellar variability mitigation, especially with F, G, and K type stars. I found that there is a lot of work needed to be done to characterize how variability can affect spectra for different types, as well as how we can use it to mitigate. But Zoe has done great work with her machine learning stuff, so definitely talk to her too. But my stuff, it shows that like we need to understand this better because it pertains to stuff talked about earlier, as well as habitable zone limits and also like the prevalence of life and if it can happen. And future work can be using geology, and if you want to talk more about it, come see me.
I think this was another one of our training.
Hello. Yeah,
Yeah.
I apologize for the background noise. I don't know if you can hear me. My name is Javier.
Hear you very well.
I'm Javier Viaña. I'm a postdoc under Andrew Vanderberg in MIT. And this is the work we've been doing in exoplanet detection using Kepler data. Basically, we trained a neural network to be able to kind of filter all the time series data that we were looking at. In order to train the network, we actually constructed the entire database to do that. So we paid a lot of attention to outliers, balancing the data, and like filtering all the information that we had, and eventually phase folding all these predictions to be actually able to retrieve any periodicity from the signals, and from there tell whether there's a planet or not. So if you're interested in this research, please feel free to reach out to me, and I'm happy to tell you more about it. I'll be staying the whole conference there. Thank you.
Hello, can you hear me?
Austin?
Yep. Hi. Yeah, my name's Austin Ware. I am a PhD candidate at Arizona State University. My work focuses on modeling the evolution of the habitable zone, so we can predict a probability on any given planet having remained continuously habitable, so we can further prioritize follow-up observations for those targets. And this work, we only focused previously on 1D habitable zone models, but we've been working on incorporating results from a 3D GCM ensemble of planets. And this is basically a demonstration of concept for incorporating those statistics to both define a habitable zone and then model the evolution of that habitable zone. Yeah.
We have Emily Witt.
Okay, we'll try to get this in later. That brings us to the end of the alphabet.
Oh, okay, great. Hi, I'm Allison Youngblood. I'm a scientist at NASA Goddard, and I have been leading an HST joint program with Chandra and XMM Newton to study JWST Cycle 1 transiting exoplanet host stars. So we're characterizing 22 of these stars in the X-ray through the UV. We're creating these broadband SEDs that are used for planetary modeling. So if you're interested in any of these planets and using our data, feel free to contact me or any member of our team. And I want to give a shout out to a postdoc, David Wilson, who works a lot on this project and just won a program to do more of this for the HWO target list in the precursor science call. Thank you.
Thank you. Going to go back and retry. We might have Sandy Jenkins on the line now.
Hi, can you hear me?
Yes, we can. Sydney.
Oh, perfect.
Hit it.
Hi. Yeah, so sorry, I'm on the train to Baltimore right now, so I hope the audio is not too bad. But my name is Sydney Jenkins. I'm a graduate student at MIT working with Andrew Vanderberg, and I'm presenting a poster about constraining white dwarf pollution mechanisms with the Habitable Worlds Observatory. So 25 to 50% of white dwarfs show evidence of metal absorption lines, which is called pollution. and this is an indication that there is some recent accretion event. So these systems provide a unique way to directly probe the exoplanet compositions. However, understanding the processes driving pollution are important for interpreting these signatures. So my poster talks about how we can use binary companions to probe the driving pollution mechanisms, specifically whether giant planets are an important contributor. And it'll also discuss how the Habitable Worlds Observatory will expand our sample of polluted white dwarfs and advance our understanding of white dwarf pollution. Thank you.
Thank you. And
Sydney.
Thank you to all of our presenters, whether here in the room, online, or on a train on their way to the room. We're very grateful to all the presenters, especially for putting up with the short time limits to let us get through those and stay on track. So thanks again to all the poster presenters. And the posters are available online on in the Slack, and they're also available in the displays here. So please make sure to take the time this week to see all the posters. Thanks again to all our presenters. Now it is our great pleasure to welcome Dr. Gaiti Hussein. Did I say that right? I hope so. The head of the science division with the European Space Agency, who will be telling us about ESA's plans for science along these lines in the years ahead. Thank you so much.
Thank you. So it's a great pleasure to be here today. I'm the next, very aware I'm between you and the break, so I will try to keep this short and entertaining. In the next 12 to 15 minutes or so, I'll just give you a broad overview of the space science program. One thing that we figured when we're deciding what to present here, we thought it's also worth describing to you how the space science program basically comes about to be defined and give some context in what we see in terms of our contribution and how we might start to support what we're talking about this week. So just a very broad overview. This is our suite of cosmic observers. So these are the missions that are really focusing on astrophysics and cosmology. Along the top, you can see the missions that are still in development. In the middle, you can see the ones that are active. You can see the ones that we're operating in partnership, obviously, with NASA, and that's JWST and HST itself. And the ones that have finished their jobs are along the bottom, and their data live on in our archives for scientists to continue to use into the future. There's an arrow with Euclid pointing downwards because it has very recently been launched and hopefully will enter operations within the next few weeks. Well, months, actually, 3 months to be precise. The Solar System Suite is also part of the Space Science Program, and this basically explores heliophysics, planetary science and everything in between, also various aspects of plasma physics. And here again, you can see the missions in development along the top and the missions in operations in the middle. And you can see we have actually a vast range of heliophysics explorers with Solar Orbiter, SOHO, Hinode, IRIS, which of course are in partnership also with other agencies. And again, there is an arrow with JUICE pointing downwards because we've had a very busy year, and JUICE in the next week essentially will enter officially its nominal cruise phase and operations. And this is kind of a broad timeline over which missions are adopted and then operated going back to 1990. The ones that are green are still operational, so you can see Hubble is essentially the longest streak along the bottom. So that's years, going from 1990, stretching right up to 2040. And the ones in pink are the ones that are currently in development, and a couple of those lines will go green. We have a very busy year, so you can see JUICE, CRISM, Einstein Probe, and Euclid essentially are all kicking off this year. And so there's a lot coming, but you can see it essentially looks like it all ends with Comet Interceptor, except that is not exactly the case. And so just a few words about JUICE. So it's going to study the Jovian system in a very holistic way. It has a vast suite of instrumentation, 10 in situ and remote instruments. It is going to reach there in the 2030s, even though it was launched a few months ago. And what its real focus is, though, is doing a comparative sort of planetology study of the 3 ocean-bearing moons, with a particular focus on Ganymede, and looking at the interaction between Ganymede's magnetic field and the Jupiter magnetic field as well. And so there's plenty of very interesting planetology kind of science that will come out of JWST ultimately as well. And this was launched from French Guiana in April on one of the last Ariane 5 launches. And Euclid is our latest mission that has just been launched. It's studying dark matter and dark energy through these vast wide field galaxy surveys. It's going to be essentially probing the last 10 billion years of cosmic history. And it is ESA-led with significant NASA participation, especially for the near-infrared instrument. It was launched on a Falcon 9, which is the other thing that brings me to the US. I was fortunate enough to see the launch from Cape Canaveral, and it's going to do exquisite imaging of galaxy shapes in order to do this very vast weak lensing survey to probe the evolution of dark matter and dark energy over the last 10 billion years, as I said. I wanted to spend a couple of minutes talking about Gaia, which is essentially the most prolific mission that we have. It is, of course, doing precision astrometry, measuring the positions, distances, and motions to decipher how the Milky Way has evolved. The last big data release was in June 2022, which essentially provided Gaia magnitudes for almost 2 billion Milky Way stars and full astrometric solutions for 1.5 billion sources, as well as many extragalactic sources as well in radial velocities and various other very useful things for stellar astrophysics. The next big data release is scheduled for the end of 2025, which will essentially cover the last 5.5 years worth of Gaia data, and then the last data release will be DR5. The last complete data release will be DR5, which will be a couple of years later. And the Gaia is enabled by the work and efforts of a very large data processing consortium spread across all of the ESA member states and beyond. And just to highlight how effective, how important Gaia has been to many different areas of galactic astrophysics. You can see here the publications per year pertaining to ESA-led missions going back for the last 10 years. And Gaia is the pink splodge, essentially, that kicks off essentially from 2018. And after Gaia Data Release 2, you can really see that it's essentially dominating our publication rates. And it hasn't quite exceeded all of the other publication rates for all our missions, but it's getting very close to that boundary. Now, I wanted to tell you a little bit about our exoplanet missions. You've already seen this plot in a couple of talks earlier today. The mission that we have in operations that has a real focus on exoplanet science is CAOPS, aiming to get very precise radius measurements for exoplanets for systems from which we already know their masses, and it's aiming to get precisions of about 10% in planetary radii. It has been extended until 2026 and potentially with options for further extension, should that be what our advisory bodies recommend. And as of this current extension, 30% of its time is available for guest observers, so scientists all over the world, and you are very welcome to apply to follow up your favorite planetary system. It's also helping identify new planets in known planetary systems as well, so it's very effective at doing what it is. This is operated in partnership with the Swiss Space Office, which is running a broader survey of specific planetary systems. The next big planetary mission that we have planned, aiming to study exoplanets and detect exoplanets, is, of course, Plato. We already heard about that in Natalie's excellent review earlier. It's going to be studying basically 1 million nearby bright stars and probing their habitable zones. It is an ESA-led mission. It requires a lot of ground-based follow-up. So if you are on any panels that need to approve ground-based follow-up, I would hope you'd be sympathetic to it, given the subject of this week. And essentially, the first field for Plato has already been identified. It's going to be focused in the south, where there are a lot of very precise radial velocity instruments that will enable to do the ground-based follow-up that's needed. As pointed out earlier, one of the core goals of Plato is to do astroseismic analyses of the target stars, in which we will then obtain the stellar radii, ages, and masses to a precision of 3% for the radii and 10%. Of the order of 10% for the ages and their masses. And with ground-based follow-up, then we should obtain fairly precise constraints on the planetary parameters as well. And so that will be launched in 2026, and it has a nominal lifetime of 4 years with potential further extensions planned. Then there is Ariel, which will of course be focusing much more on atmospheric chemistry and the thermal properties of thousands of exoplanets via transit spectroscopy in the infrared. And again, this will require a lot of ground-based effort. And so that is something that is currently in the planning. It'll be launched in 2029, and piggybacking on that launch, we'll also have a Comet Interceptor mission, which will be studying, which will wait to study a long period comet. Now, I wanted to spend a couple of minutes just towards the end of my presentation, which is talking about how we go about doing strategic planning. We have had various calls for ideas from the European member state communities going back to the 80s. So the first round in which we collected ideas and selected missions by essentially probing where the scientific priorities of the ESA member state communities were in Horizon 2000 and Horizon 2000 Plus, which was conducted in the 80s. And you can see a list of the really seminal missions that came out of that. We are currently towards the tail end of what we call the Cosmic Vision exercise, which was kicked off in the mid-1990s. The missions that are already well on their way to operations, if not already in operations, are underlined. So JWST, Solar Orbiter, Euclid, and Cheops. Ariel and Plato and Comet Interceptor are well in their development phase. Envision is really starting off its development phase. LISA should be adopted early next year, and Athena its time frame is to be decided later on this year. Out of these exercises, we also got approval to essentially go in partnership with partner agencies, and HST, JWST, and SMILE are excellent examples of that, along with more modest contributions to various missions of opportunity, which are all listed at the bottom of the slide. We are currently kicking off what we call Voyage 2050. This was an exercise which was started in 2018, where the ESA member state communities were invited to submit white papers on what the current burning scientific topics are that would fit within the ESA Space Science Program. Almost 100 white papers were submitted. 5 topical teams were formed covering the broad range of science that ESA serves, and they reported to a senior science committee, out of which 3 to 4 main large themes were identified for which technology development would be required, as well as a number of concepts for medium-class missions, which are of the order of 500 million euros or so, and priorities for partner contributions, which brings us to the most relevant part for this week today. For the L-class themes, the 3 big themes that were identified were to do with moons of giant planets, essentially a successor to the JWST mission, to go and visit an ocean-bearing icy moon and really probe the connection between the interior of the moon and its surface. So doing tomography along with looking at, with much more sensitivity, at prebiotic chemistry, potentially including a probe. And that is currently what is already started being studied by an expert scientific team that has been convened. The second theme for a large mission is looking at temperate exoplanets, really going into the mid-infrared potentially to get the, to essentially characterize the atmospheres of temperate exoplanets in detail. And the the study recognized that this was a particularly ambitious theme, so it's really looking at, okay, we need to look at the difficulty of this technologically, and another possible option is to do a follow-up of Gaia in the near-infrared, and essentially complement Gaia and essentially probe, complete the survey, essentially, of the Milky Way. And then going further, the concept for the third L-class mission would be looking at physical probes of the early universe, so really probing into redshifts of the order of 1,000 and beyond. The study also recommended that ESA member states should look into providing contributions, as we have done in the past, to partner-led missions, doing things together that we clearly cannot do with ESA's budget alone, and within that, HabEx, I just combined them the other way, were of course mentioned, as was LINX, but also a potential mission to Uranus or other missions as well. So we're looking within that. So the next steps essentially are, we have a new envelope of budget that was defined for us at the end of last year by our member states. And our advisory body, the Science Programs Committee, will be meeting in November this year, and they're going to be defining the long-term plan that essentially allows us to start spending that money in the next years. Ahead of that, though, given that the activities are starting for this particular mission, the idea is, we've been discussing with our partners in NASA what would make sense, and we will be going out with a call for people who are interested in contributing to the scientific efforts of HWO towards the end of the summer, and for European scientists to come forward and put in applications for that, and then ex officio, there would be an opportunity for them to join the START team activities. I don't know if this microphone's working, but voice has gone weird. In any case, so that is essentially broad strokes of where we are today, and I'm looking forward with interest to hearing how things are shaping up for HWO. And if you have any questions about the ESA Space Science Program, I'm around all week. I'm really happy to take your questions. Also, in picking up on a question that was earlier, I also have a background in stellar magnetic fields and planetary magnetic fields. So if you have questions about how to detect exoplanet magnetic fields, feel free to come and talk to me about that too. So thank you very much for your time.
Thank you so much. We certainly have questions now. Time for questions from the audience. I know we're headed to coffee. Here we go. Jennifer, and then one in the back.
Thank you. Jennifer Wiseman, NASA Goddard. I got a little confused that you had the cosmic vision that supposed to go through 2025, and then the Voyage 2050. So do you have another visioning program that's going to start with 2025, or how do those mesh together? Yeah.
So it's continuous, right, essentially. So these Envision essentially will be launched in the early 2030s, essentially. So it is continuous. We just need to, there were priorities and particular themes that were identified in the Cosmic Vision exercise, which was already going back to the 90s, right? So we had to refresh, to scan the horizon. We need to continuously be doing technology development. We have a separate tech directorate, which is also looking at technology development continuously to support what we're doing in the program directorates, as we call them. So the Space Science Directorate is a program directorate, as is Earth observation and human robotic exploration. So it's a continuous development that's happening, but the community is consulted broadly every decade or so.
Got it. Okay, thank you.
Jeff Booth from JPL. How do you anticipate the interaction between ESA and its member states, CNES, OSI, et cetera, for the potential activities or contributions towards a mission like HabWorlds?
It's a good question and a tough question to answer directly. So there is clearly interest in in several of our key member states in joining Habitable Worlds at different levels. And that is clear. We are very aware of that. At this stage, we don't have a clear position, because we need a clear position from all our member states of exactly at what level they want ESA to be contributing to that. And because the Space Science Program is a mandatory program, all 22 member states have to agree on those priorities. Of course, individual member states are very welcome to do additional things on their own, as they do for several missions. And so that is always an option. What we're hoping is that by November, we'll have a very clear plan of what the envelope is and what our time frame is on how ESA can act in the next years. And then, of course, there will be discussions with CNES, DLR, all of the other partners, ASI, to see what they want to be doing. And of course, there are bilateral relationships between them and NASA as well, which are not really our business. But certainly, I think what everyone's waiting to see on the European side is where the ESA member states plan their priorities, and then everything else will, I think, shake out from that.
Other questions in the room? Do you have questions online? Great.
Hello? Oh, it is. All right. Carl Stoppelfeld, when will ESA start the concept study for that Voyage 2050 recommended for the mid-infrared exoplanet spectroscopy mission?
Very good question. So essentially, I would ask you to check back in around November time, when we should have a much better idea of our timescales, because we have a number of missions that need to be decided. So basically, LISA will likely be adopted early next year. The timeframe for Athena, as many of you might be aware, has been rediscussed. The scope of it is being rediscussed. And so there are decisions that are being made on Athena towards the end of this year in terms of the science it's going to be delivering. And there will be a number of timeframes that will then be decided on the back of that, because obviously we need to focus on delivering what the priorities are in the pipeline, and that will determine the timeframe of what comes next. So come November, we will have a much better idea of what the long-term planning looks like. But at the moment, I can't answer that definitively because we're waiting for those answers. The other thing that needs to happen in November is we have a number of phase 0 M-class studies that were kicked off last year. And there's 5 at the moment. They'll be whittled down to 3 main themes. So those will be selected. And then those also have to fit into our long-term planning. And it's just about managing our budgets responsibly for the next years.
Any other questions? Great. Go on.
Maria Kristeva, will the summer call for European scientists also include European technologists?
At the moment, it's focused on scientists, but of course, it's a good question, actually. What we might do is ask for people to express interest on that side, and then we'll talk about how we can manage that. But for the START team, we're really focusing on the science effort at the moment. But I know there's interest in technology development, and I think that's certainly something we can look at what we get and then see what we do with it.
Any more remaining questions? All right, well, let's thank Dr. Singh once again. And I think we should also, take advantage of the moment to think about the augmentation of the science fleet out at L2. Bon voyage to Euclid on its way out to join JW and Gaia out there. Congratulations. I believe we now have a coffee break. Is that correct? We will come back in 20 minutes. Thank you all. Right.
Yes.